Okay, our next talk is a tutorial on building trustworthy AI. It's by Jessica Schrouff. Jessica is the Director of Responsible AI at GSK, where she leads the ethical deployment of AI in healthcare. And I know many of you are interested in healthcare, so hopefully, yeah. Previously, she was a research scientist at Google DeepMind, where she specialized in fairness, interpretability, and robustness of machine learning models. Please join me in welcoming Jessica.
Thanks, Ibrahim. Hi, everyone. I know it's the last day, but yeah, I hope you're still up for this and that you had a great time yesterday. It was a really fun party, so thanks for having me over. So following up on the talk from Hamid, actually, this was a great intro for this. But today, I'm going to take maybe a bit of a deeper dive into fairness in particular. And then we'll see maybe how this relates to some of the other fields, because when we talk about responsible AI, trustworthy AI, safe AI, then we can get in a bit of a mumble jumble of words, and I'm going to try and clarify a bit what it means, and especially with a lens on fairness. But before we do that, because this is well, winter school in this case, I find it fun to just explain a little bit, kind of like my career steps. And so basically I did not train in computational science. I trained in electrical engineering because there was just no such thing as a machine learning degree at the time at my university. And I applied mostly machine learning methods for neuroscience. So at the time, deep learning was not really a thing. And it was not possible to claim to do artificial intelligence by calling a model on a web app. But yeah, this was the fun times of linear models and probabilistic models as well. And I encourage actually all of you to not forget these times when you do learn about machine learning and artificial intelligence. It's quite easy to get drawn into all of the LLMs and those services that are out there, because it's also what's kind of hyped in some of the main machine learning conferences and research centers at the moment, but quite driven by industry. But I can only encourage you to go back to these fundamentals, because they do drive a lot of the innovation, and they're quite critical in how we can make those technologies advance as well. After that, I did a postdoc. I actually spent quite a lot of postdoc time. I did like it, didn't know what to do next, so postdoc was great. And I was split across medical, so actually working in hospitals and slicing brains, which was fun, and in computer science department. And then I went into industry. I joined a startup in 2018, and they were doing AI for code, so trying to generate code with AI. Now it seems like, yeah, this is kind of almost a solved problem, but back then it was very early days. And they took this nice approach that was trying to frame any kind of piece of code as an abstract syntactic tree and use the structure in there rather than use it as text. And their main competitor actually was Microsoft, trying to do that with LLMs at the time. And then obviously with the bigger amount of data with Microsoft owning GitHub and stuff that they had, then Microsoft with the large amounts of data, large amounts of compute, then it kind of took over, and the startup went over. But I'm still quite curious about whether with more data, with more compute, this approach of using the structure in the code could actually have been quite informative. And in a way, it's kind of what drives also a lot of the work that I do, and especially in responsible AI, is how we look at the actual way data is generated, for example, and use that in our modeling stage, or to understand what we really need from the model behaviors. So yeah, after that, I joined DeepMind, Google Health. I did mostly AI for healthcare. And very quickly switched on to looking at the impact of the models in society. So interpretability and fairness were like main topics. And because of all of the questions they raised, they just have, they have stayed with me. And I've managed to convince a few people to jump on that bandwagon. So hopefully I'll convince some of you today as well. We'll see. So yeah, so those three words, actually, Hamid mentioned them in the same sentence. Like a model is like safe, trustworthy, or responsible. And to me, they actually mean quite, like they're used interchangeably, but they can mean quite a few different things. And it's going to depend on the context of that as well. So they're also very hard to pinpoint as one thing. Like for a certain context, what does it mean for a model to be trustworthy? Are you going to trust the predictions of a model for like a medical disease if it doesn't work for certain types of populations? And so like we can think about these terms are kind of being a mix of those underlying concepts and actually valid constructs that we're interested in, and that this mix is going to depend on the context that we're looking into. And so, like Hamid mentioned alignment quite a bit, and obviously if you have fairness as a value or equity as a value, then obviously fairness is kind of a bit of like that alignment as well. And we're going to see how those different terms also interact quite a bit. But I'm going to focus a bit on fairness. And so just as a kind of like setting up the stage, who has, I know some of you have worked on fairness, so who has like, heard about fairness or learned about fairness or applied fairness metrics to some of their work? Actually, not that many, so. Okay, who wants to maybe give a definition of fairness? Yeah, go ahead. Yeah? Yeah? Do you want to give one? The opposite of bias. Okay, that's one. Anyone else? Mm-hmm. Good. Yeah, good. Yeah. Another one? Sorry, I can't hear you. Ah. Thank you. This is, so, I mean, in a way, they're all valid, right? And fairness is very hard to define. And in a way, that's why I go the easy way, and you'll see. So, like, just a brief description of how, like, we have, like, these AI principles, and you'll see, like, major companies have AI principles, and how they relate to all of these dimensions that we actually want our models to abide for. And so one is like no unfair bias, which is what was mentioned as one of the definitions for fairness. But my easy route is not to define fairness, it's to define unfairness, because that's easier. So, and in this case, I say, and again, I don't put a strong equal sign, but I say it's kind of looking like unfairness is when there are disparities in model outputs across demographic groups. And I'm not necessarily talking about just predictions, and I'm not necessarily talking about performance necessarily, right? And we'll see the difference in that. So there have been quite a few examples of unfair models that have been deployed. So we have in the criminal justice system, we have the Compass data set, like the Compass study that was quite famous, showing that black defendants were at a higher risk of being denied. Basically, it was influencing whether they could be approved for bail by a judge. They were shown at higher risk of reoffense than white defendants. In the hiring system, so Microsoft had a screening system in place where for every resume they received, they would like have kind of a chance of like success at the company that was predicted, and that for the same resume with like males or female sounding names, the chances for females were lower. They retired that. Well, they claimed they did. And in medicine, and this is kind of like where I'm going to set the example, because obviously like I've been working in healthcare for a while. Then in medicine, there's this example where it's a study by Obermeyer et al., where they basically, it's based in the US healthcare system, and they tried to put in place a high patient care management system. And so this was like an insurance company, a healthcare system, and they wanted to identify patients that had poor health so that they could manage their care, give them tips on how to be healthier on a day-to-day basis, so that they didn't have to come back to like the emergency room too often or need like very expensive care or get very sick, basically. And so like this enrollment was based on an algorithmic system. So you would, based on the patient, predict the risk of them having like severe health needs. And if the risk is quite high, you would enroll them in that care management system. It is resource constrained, obviously, like a lot of things in this world, where you don't have a lot of places. You have to define the threshold that's quite high for patients to be enrolled, because you cannot help every single patient. And so what they did is, like, because you don't really know a patient's health needs directly, they used like a proxy for that, and they used the money that was spent for those patients. So all of the tests and all of the bills spent by the insurance basically on those patients, and those was like approximating their health needs. Now, this is a figure from that paper, and on the left-hand side, what you can see, is there a pointer in this? Okay, so on the left-hand side, so you can see here they're plotting the risk score from the algorithm at the bottom, and the y-axis is another kind of like proxy for health needs, which is the number of chronic conditions. And what you see is that for white patients, they actually have less chronic conditions for the same level of risk than black patients. And the vertical line on the right-hand side is the defaulted into program. That's when patients actually get admitted into this care management program. And you see that patients, like black patients, need to be sicker than white patients to be admitted into that program. And on the right-hand side, they made a simulation of if that bias had been corrected, what's the percentage of black patients who would have actually been enrolled into the program? And we see that it would have been much higher, right? So what happened there is that basically money was just a poor proxy for health, because there are so many other factors that came into play between how much you actually spend on your health and how sick you are. And in this case, there are, not everyone has the same access to healthcare. For black patients, even with the same needs, sometimes you have lower expenses, and you have the case where black patients are regularly denied paid medication, for example. Black patients can be more ill when they become treated, also because of this unequal access. And so it turns out that this label, cost, is quite biased. So this is just an example, and you can see how different, biases in society can impact the outcome of these algorithms. So let's look a bit at other examples of sources of unfairness and see how they kind of interplay together, but also basically focus on where we are, us as machine learning developers, and in that kind of like ecosystem, and what is it we can actually do. So, not going to surprise anyone here. This is actually quite like a figure from a paper that I found. It's quite a niche paper, but this discussion on biases was actually quite nice. So I've borrowed the figure. So yeah, not surprising, there are biases in society, right? This is kind of like a given now, unfortunately. So you have quite a few examples of this, like, you know, screening programs are not available to everyone. Clinical studies have actually excluded certain groups. I've worked in neuroscience, and we were excluding females because, you know, they had periods. And it could throw off the results from an fMRI study. So understudied health issues as well, whether it's actual disease, whether it's disease regarding certain populations, so women's health is understudied as well. And biased clinical training, so that came out from another work that I did on dermatology. And actually, in this case, like the dermatology textbooks mostly use pictures of skin lesions for very like light-skinned patients. And so doctors that are like trained with those textbooks can have trouble with identifying lesions on darker skin tone patients. So obviously these biases in society leads to biases in how we record data and what type of data we record. And so we end up with subgroups being poorly represented, biased labels, data that's not missing at random, and the granularity of data that we have for certain populations is also quite different. Now, this is where we come in, which is the model building part. And so there's often this kind of hypothesis that, you know, it's like crop in, crop out. And so if you have biases in your data, then you're going to have biases in your model. But if you have good data, then, you know, nothing you can do is going to change that. And here I'm going to go against that because there is actually a lot that we do as machine learning developers that influences the output of the models. And, you know, like basically our choices are driven by our values, by the values of the companies that we work for. And obviously this all has an impact. And things like which metrics we actually optimize when we train our models, if these metrics actually have been selected on the direct, like the actual impact it's going to have in society, or whether, you know, like you build your model and you have a good AUC, that sounds great, but actually what you're actually deploying is a risk score system, and so AUC is maybe not the best metric for that. Things like training choices, so regularization is going to impact the fairness of your model, and it's going to depend on what signals your model are going to focus on first. So you can have simplicity bias, where your model starts by learning the confounding signals really quickly. And if you use early stopping, then you're going to prevent the model from learning the more complex signals. But on the other hand, if you have really good, sufficient signals and you do early stopping, you can prevent the model from overfitting to some of those like more confounding signals. So you see there's no like one rule fits all, and all of the things that we do really influence the type of output we have. And similarly, like even a model that has very similar performance, if you train it from different seeds, can have different fairness properties. So, you know, even if you, in most machine learning papers, when you report variability across seeds, like I don't think I've ever seen, like outside of this paper that actually like shows that point, I don't think I've ever seen another paper that shows like not only just performance across seeds, but also other aspects of the model. And this is another thing to be aware of. So all of those factors will impact the fairness of your model, and you do, as a developer, have a hand on that. Sometimes, like, especially when you work on fairness, sometimes it can be difficult to have discussions because it's like, oh yeah, but you should just fix the biases in society. I'm like, well, I wish I could, but obviously I can't. But I do have control over that bit, and this is maybe one of the things that I would like you to take out from this talk, is that, even though we don't have control on the overall system, we do have control on bits of it, and it's important of being aware of how all of these pieces kind of fit together in the larger ecosystem, and not be like, oh yeah, but I just trained the system, right? So yeah, so the last bit of this is biases in deployment, and you have things like, people will trust the system differently depending on where they come from and what type of education you provide them to use the system as well. And that can lead to, again, downstream impacts that are differential across populations. And obviously, all of these, they feed into each other. So when we deploy a system, then we're going to get more data in, which we're then going to use to train another system or update that system. And then this can have long-term fairness impacts by how the system impacts society in itself. So it's really important to consider all of the steps in the pipeline, but also how the pipeline is then going to interact with society and think about these long-term fairness impacts. So now that we've talked about, the sources of unfairness, how do we measure unfairness? And there are a couple of families of fairness metrics I'm going to go over in a bit of detail. I'm splitting the kind of criteria, so something that we want versus how we implement it. Because again, there are, it's kind of an approximation that we're making when we're using a fairness metric, and it's not necessarily that it represents exactly I'm going to say value, it's maybe not the right word, but that we want to approximate here. So the most common fairness metrics are statistical group fairness metrics. So it's looking at differences in model output between different subgroups of the population, like treating those subgroups as wholes, and then you just compare between subgroups. So for that, I'm taking the more formal notation where you have it's a prediction system, so that's a bit easier to look at. And I'm gonna, you also have the regression version with an output, but basically you have a label y, and then you predict y hat or a regression score. And then you also have a sensitive attribute, which I call A. And you may or may not have access to input features, which I'm calling X. And so for this first criteria, it's actually the easiest one of all. It's just basically everything that comes out of my model should be independent of my attribute. So this is kind of this independence criterion. And we can think of equal acceptance rate. So we implemented through different metrics, and we have statistical parity and disparate impact here. If you have multiple subgroups, you also have questions about how you're going to compare those multiple subgroups. Are you going to take the maximum between any pair of subgroups to identify the worst case scenario? This is quite common. Or are you going to look at any other kind of comparison? Or do you have a majority group that you want to compare other groups against instead? And how you balance that with the distribution of your demographics across that population is another factor. So you see the way we even implement a fairness metric can affect the result we have in the end, right? And we do need to make quite a few choices, again, as model developers, of like, do I look at the maximum? Do I look at kind of an average? Do I look at the deviation from a majority group? Like, all of these are actually quite tough questions to answer, and they're best answered probably not by a single person, but often, you know, being realistic, of course, we would like to have all of the stakeholders involved, but being realistic, it is often not the case, right? So even being aware that those metrics are just an implementation of a specific criterion that was chosen is, again, like an important factor in what we then, you know, the importance we give to that metric in the end. So another type of group fairness is what we call separation, and it's more around equal error rate. And so for that, this tackles the case of when you don't have the same prevalence of the label between your subgroups. This is quite common, actually, in healthcare. And so we just say that condition on the label, your predictions should be independent of your attribute. And for that, we have equal opportunity or equalized odds, and it looks at like TPR or TPR and FPR, and again, the way it's implemented, you're gonna impact the actual numbers you get out of it and maybe your conclusions. And then the last statistical group fairness is sufficiency. Wait. Oh, yeah, no. So this one was just around, like, again, like exactly how you would then implement those. And comparing ROC curves per group is also a fairly common one. So, yeah, so the last one is sufficiency, and it's equal outcome frequency. So in this case, it's you kind of revert the conditioning. It's like, given a model prediction, I want my labels to be independent of the sensitive attribute. And so in this case, you mostly look at comparing PPV and NPV per group and calibration curves per group. There are other techniques maybe more advanced, but these are, like, even just looking at calibration curves per group is not kind of a standard. It is somehow like more classical in the medical, like purely medical sense, when they don't even do machine learning, but just like look at statistical fitting, or just like even they do like linear regression sometimes, and they look at calibration curves per group. It's actually quite common in that field, but in machine learning, it's not that well spread. And so to come back to the bias in EHR case that I was mentioning, that we can see that a metric around calibration curves per group would likely have solved that issue, right? And this is actually what was suggested in the paper to obtain this simulated curve on the right. And this then was corrected, actually, by the provider of that algorithm. And they did redo some calibration afterwards. Now, we have what we call impossibility theorem. It does come with some caveat, but here, just like the main idea is that these, like by definition, you cannot satisfy all of the fairness criteria simultaneously. So if you have an example with like different prevalence of the disease per subgroup, and your classifier is perfect, it is not going to be independent, just because you have that difference in prevalence. Now, we do not have in practice perfect classifiers, and we've seen that quite often when you improve on a fairness metric, you can also improve on other fairness metrics. So again, this is not like a very exclusive result that should be taken as, oh, well, if I just pick one fairness metric, then I should forget about the others, because actually you can look at the others and you may improve on the others as well. Another type of fairness is individual fairness. So it's looking at similar individuals in your population but that have a different sensitive characteristic, and then looking at if they're similar, but they just have this different characteristic, then they should have similar outputs, right? And so the critical choice here is how to define similar. And that's why this metric is maybe not as well described, because actually that choice of these like two metrics, it can be quite difficult to make. And again, includes a lot of like how you define similar, individuals can be quite value-laden and can be, quite impactful downstream as well. And finally, we have causal fairness. So this is based on causal interventions or counterfactuals. So this is not equivalent to replacing an attribute in your input, even though a lot of papers claim that. It is based on the causal inference mechanisms. And in some tasks, actually, like group fairness criteria do match causal fairness criteria as well. So what I do really like about this approach is the what if question. What if this individual had been, like born earlier or later, or had been like female instead of male? Like, obviously, it's not like you can't turn an individual from like female to male, right? And that doesn't really make sense to do so. But if you're looking at, would they have, like the example I gave about the resume. So, for example, like females do take more time off for childcare. And this is like not always a choice, right? It's just like even our government tell us, like in a lot of cases, that females do have to like take time off for parental leave. They have more parental leave than males. In Belgium, where I'm from, it's 4 months for women and it's 3 weeks for men. So don't really have a choice, definitely impacts the resume, right? But if I just change the name on the resume, I still have a lot of absence. It's not really the same as if I had been the man in that couple who had a kid and I had continued to work. So this counterfactual question is where, okay, if I had been male, then that would have changed a lot of my features and my attributes. But if it's not affecting my label, then like I want to know that I have the same output, right? And so this is really the question that's asked in causal fairness. But obviously answering the what if question is really the tricky bit here. And there's a lot of like mathematical tooling that can help with that, but it's still hard to really scale. So, we talked at the beginning like around like safety, trustworthiness, responsible AI, and all of these other fields like interpretability, robustness. And so obviously there are a lot of relationships there. And actually there was a really great tutorial at NeurIPS. I hope the recording is still up in 2023 that I recommend to everyone. And obviously like fairness and especially statistical group fairness, like you can think, okay, well, it's similar to robustness to demographic shift. So if you have a change in the population, you want the model to be robust to that. And so in the same way, it's kind of like ensuring that the outcomes are the same across different subgroups. Like counterfactual invariance to sensitive attribute. So that's like, again, like a robustness type of factor based in like causality that directly relates to fairness as well. And robustness methods have been used directly as mitigation for earned fairness fairly recently. And they've been shown to be quite efficient. So it's not because you work on fairness that you can't look at robustness methods or even causality-based robustness methods. And in the same way, things like interpretability methods. So there's often of like, I'm going to look at the importance of demographic factors in my model. So this obviously relates to that as well. And what we need to really keep in mind here is that different methods will yield different results based on the assumptions. And it's true for interpretability on its own. It's true for all of these kind of metrics that we're implementing. They're obviously the, like downstream result of a lot of choices that we make. And that's why thinking about these relationships, but also thinking about how we can exploit the fact that we have similar but slightly different metrics that measure what we call maybe the same type of construct is interesting to exploit, because then we have multiple tools to look at the same thing and can like try to narrow down the issues that we are facing when we're developing the models. So one of the last aspects here is fairness versus equity, and this is coming to that like pink image that we had earlier around deployment, because as machine learning engineers, right, we often have access to the labels or any kind of outcomes that we have, but we don't necessarily have access to what's happening in society right now that may be unfair. How do I measure that? How do I compare what I'm going to put out to that? And this is why basically there is like no automatic trade-off between fairness. There's no relationship between fairness and equity. There is a relationship, but it's not a direct relationship. And also this is important to remember, that there's no automatic trade-off between fairness and accuracy. So there are some papers that said, oh, if you're making a model more fair, you're going to decrease on accuracy. There are a lot of factors that can play into that role, including the choice of your test set. But I think here, what I would really like us to focus on is the relationship between accuracy, equality, and equity. So I have this kind of like little like toy plot of like, okay, this is basically what's happening in the world now, where we have 3 demographic subgroups, and the outcomes from those subgroups are that basically like group A benefits more from whatever is out there in the world than group B or group C, right? So now I add AI, and I'm like, oh, AI is better than what's out there in the world. We should definitely use AI. And then you look at actually what's, the fairness of your model. And the fairness of your model is not that great. And if we had access to what's happening in green, like you would actually realize that you're going to, improve the situation for everyone, but you're going to increase the gap between A and C. So you're going to increase inequities in this case, even though you're going to benefit everyone. Now, if you deploy a fair model, no, this one is, sorry, I'm getting confused with the slideshow. So in this one, you're going to have equal benefit. So you're benefiting everyone in the same way, but basically it's the status quo. So group A is still better off than group C. So yeah, it's like, yeah, okay. Is there any other option here? So one option, and that's the ideal case in a way, although it could be hard to discuss, all of them will be hard to discuss with anyone anyways, but like, potentially my ideal scenario would be this, where AI actually benefits everyone, but kind of counters the inequalities that are present in society. And there is one paper actually from some colleagues at DeepMind, Google Health, who established this method that we're looking like, basically they were aiming for an inverse correlation between what's out there in the world and what the AI was doing. So we're trying to really correct for biases there. Obviously, has a lot of caveats, but this is still like a, thinking about equitable benefit, while this reduces the benefit for group A compared to how much benefit group C gets. Now, what could happen is that your fair model is not going to improve for everyone. You may not have benefits for group A, in this case, it's actually you're going to reduce saturation. So you're kind of reducing the privilege of group A, and you're going to increase the benefit. You just have benefit for group C. And then everyone is you know, equal. So yeah, how do you, like, if that's the case, how do you, like, what do you do with that, right? Do you actually deploy that knowing that group A is going to be really pissed at you? Maybe it's just the fair thing to do. It's repairing inequitable treatment in society. But obviously, you're going to get a lot of pushback from group A, right? So yeah, do you know, delay until you can further down estimate the impact? Do you deploy for do you only deploy for subgroup C? In that case, you don't deploy for A, so it kind of like stays where it is. So these are all really tricky questions. They can be like other mitigations to look at. But this is, in a way, it's kind of like the fun thing with fairness, is that there's no clear answer. And it's very important to talk to a lot of people actually involved in this. It's really important to talk to group A, B, and C, and anyone involved in that model that you're going to deploy. So now we can think about, you know, like, okay, this is all good and well, but everything we've talked about is mostly about like this kind of like maybe disease prediction model, which is like a basically binary prediction with like a binary attribute. And so is fairness still like relevant when we talk about alignment, when we talk about, you know, like in the scheme of RLHF, do we really care about fairness? Well, I mean, again, no surprise here. I'm going to argue that, yes, obviously we do care about this. It is very hard to measure. So there are benchmarks and like various methods for LLMs, for example, that will look at, you know, stereotypes or representation harms, or what if I change the pronoun from he to she? Do I have a different output? But typically this is really focused on single instances and not at like the whole patterns, and it's not looking at the full distribution. So I would say that in that case, like really thinking about fairness metrics remains important. Now, obviously, like how we extend all of those fairness metrics into those more complex setups, like does remain like an open question. It is really hard to think about, well, okay, it's easy if I go and change the pronoun, but how do I actually measure the outputs there? And I think this, again, like when Hamid was talking about these models being really well aligned, I guess this is a question that I still have, because there are quite a lot of cases where you can ask a model, like, would you make any difference for like a resume if the name is female or male? And the model would be, oh, no, 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 this would be bad and stuff. And then you actually give it PDFs, right? You give the PDF of a resume, which is slightly different because then it needs to go and read into this like PDF document. It's different than just giving the text. And you can also give an image, like a JPEG of the PDF, which might give you even like different results. And then you actually see a difference between how it treats the same resume with a female or a male name. So like, is that alignment fairly superficial? Is it just that we don't we don't cover the space of what can be evaluated in those general purpose models? I guess the question is still quite open. So as, you know, conclusion, you've seen that there are still a lot of things that need research in this field. So I've briefly mentioned long-term fairness. This is a very open aspect and field of research. Taking a causal lens, I mentioned all of the methodological difficulties with that. The relationship with other fields have been somewhat explored, but can be further explored and exploited as well, because there is a lot of, you know, improvements made in other fields that could benefit responsible AI. Yeah, biases in LLMs, but also in agents, And when you have multiple agent systems with sequential decision making, how you estimate fairness in that. How do these compound? And also, obviously, not the ethical, but also not the technical, but also the ethical considerations, right? And so it's a very challenging and interdisciplinary field, which makes it very fun to work with. And yes, and this is my recruitment slide, because like diverse and inclusive teams lead to better responsible AI, and it's been shown, so you can claim it. It's been shown that responsible AI leads to better models as well. So as you are starting your career or on your path to machine learning and artificial intelligence, I highly encourage you to think about these aspects and see if like the type of impact that you'd like to have in this community and in society at large as well through the technology that you develop. So yeah, thank you all for your attention. Take any questions?
Yeah, thank you, Jessica, for the exciting talk. I hope you're convinced by now that responsible AI is a lot more exciting, more intellectually stimulating, and potentially impactful to human lives than just doing better on ImageNet and other benchmarks. So we have time for a few questions. Please, go ahead.
Thank you for the great talk. So yeah, I'm already convinced about responsible AI before this talk. So. My question regards the performance metrics, very common one, accuracy. Usually, the papers focus a lot on the accuracy and don't consider the other metrics. But at the same time, considering trustworthiness in general, either fairness, reliability, interpretability, and so on. If we take a model that is highly accurate and doesn't perform very well in terms of fairness or in terms of reliability, uncertainty quantification, and then we compare it to another one that is that gives a good uncertainty quantification, but it is 70% accurate compared to the other one that is 90%. Would you qualify the first one as reliable, more reliable, or the other? 90% accuracy with sometimes good hallucinations, or 70% accuracy with really high and good uncertainty quantification? Which one is more reliable?
Yeah, I mean, this is a critical question, right? And there's not going to be, it's going to depend on what's your test set to get those numbers, what's the distribution of the populations in those test sets as well, what is the downstream application, how are people actually use that information that you're giving me now to compare these two models, for example. And yeah, it is really tricky to find, to do model selection at this stage. And that's why things like really estimating things I forgot the word, but where you put your model, you deploy your model in the wild, but you actually don't act on the decisions, for example, right? And you compare to the downstream impact it would have had. And there's also another thing that's eliciting model preferences. So, because again, as model developers, it's unlikely that you will make on your own that decision. What we actually need to think about is who's going to use the model, and would they prefer one versus the other, and how can we maybe measure which one they would prefer. And so there are techniques like that where you actually, it's a paper, it's Sami's paper actually, where they were doing comparing with users with a confusion matrix, and they were would you prefer this confusion matrix or that one, right? And it would actually show how people would prefer their errors to be distributed, and then they had kind of a function for each person basically, which was really interesting. But yeah, there's no direct answer, and I think the answer should be it needs to be a complex process to make that choice, right? It shouldn't be a like, oh yeah, for sure, just use the more like accurate one, because obviously it's going to perform better. Actually, no, it's not clear, right? So.
Okay, thank you. I have time for another question or not? A very quick one.
Okay, if it's a quick one, because
Good
I have
negotiation.
2 more questions.
That's a long line. Okay. Like it's almost the same, maybe the same answer, but just like how we decide on the trade-off between egalitarianism and utilitarianism in terms of fairness. So it's all, like, does this first answer also reply to this question? Like, depends on the scenario? Like, either maximize the average fairness between the society or, let's say, help the poorest?
Oh, yeah. So you will encounter a lot of like utilitarian people in the field. I am not one of them.
So you are more in the egalitarian.
So yes, I do. My direct manager is utilitarian, like a very strong utilitarian. We have a lot of passionate discussions, let's say. So yeah, I mean, obviously, you know, when people come to me and be like, you should solve inequalities in society, I'm like, well, yeah, like we have a way to do that, right? Like, and actually, maybe it's not using technology at all. And even like sometimes when asking that question, you do get a lot of pushback. But yeah, because there are a lot of other interests at play, I guess. Okay. But yeah.
Thank you.
That's my answer.
Yeah, thank you for your talk. I'm very interested in this field. So I have a question. I read a lot of papers on this topic, and I have a feeling that a lot of research in this direction starts with an assumption that our models are already biased. So we always assume that, yeah, our models will definitely perform better for white people than black people just because we have more data for white people. But it's not always the case, because sometimes just these demographic attributes like ethnicity are not related to the disease or the disease of interest that we are considering. So I just want to know your take on this, because I see that this assumption drives a lot of research, and sometimes people spend a lot of time doing a lot of experiments, and then they end up reaching a point where, yeah, we didn't do anything because our models were not biased in a sense. And should we also consider not predefined attributes for disparities, like just look into our data to cluster or to find out what our model are biasing against? And one final question, can we say that the fairness problem just all points out to our unfair data? So if and at any point we were able to just get more fair data representing all ethnicities and all demographic attributes, can we say that we can solve that fairness problem?
Thank you for the questions. Okay, so on your first 2 questions, I guess there's so we can think about like confounding factors in your data and your models, right? And the impact it has. I think that there is, well, first there is a lot of evidence that our models are biased. They might not all be biased. They might not all like sensitive or demographic factors be relevant for all cases. But we have seen that, so it's better to be aware and then find that they perform equally than not even look at it. And so there are also like legal bases for that. And that's why it's really interesting, because the legal basis is going to be different from country to country, right? Like, what is a sensitive attribute depends on the context. And when you mention like it may or may not be relevant for a certain disease, this is where this context really comes about as well. And how to find those confounding factors or those sensitive characteristics that may be relevant. Like, you have a lot of research that's to try and find these automatically. Like a Bayes, like clustering and embedding is going to do like somewhat do that, and you have other ways of doing that. But also like based on diving deep into the application and talking about to all of the stakeholders is where you're going to understand some of that. So when we do healthcare applications, we talk a lot to like the medical practitioners and the medical experts as well, to try and actually get that what should we pay attention to? But like a lot of medical education, you know, like medicine is also a constantly evolving field, for example, and it's not, we do learn from things all the time. So actually there was this kidney injury prediction, and it relies on a marker in your blood that indicates whether you're going to be really sick or not. And that marker is corrected based on race. I think also age and sex, I don't remember exactly the factors, but it's corrected. And there's like a big debate in the medical community on whether to use that correction or not, because obviously the correction impacts our labels, and that then impacts like when people actually get sick. And so I think the questioning remains important, because what we may find is still kind of up for grabs in the sense. Yeah, I'm trying to remember your third question.
Maybe I can leave time for
Yeah, we can talk offline.
Hello, Jessica. Thank you for the great talk. My name is Hiba. I work in AI fairness in healthcare too. So my question is, considering your experience, things like the impossible theorem, the high variability in results among seeds, do you think it is realistic to push research and expect good results from general models? Or do you think we need to like stick to more demographic specific models?
This is a great question. I think there are conflicting incentives there, in the sense of, obviously, it's tricky to have like demographic aware sometimes models, because then you would need to have the demographics as an input to your model. You may not have the access to that. So there are like practical limitations to that. There are legal limitations to that. So France, for example, prohibits any kind of recording of demographic attributes, just because, you know, like, if we don't see it, then it doesn't exist. But I think maybe to turn your question maybe slightly, one thing that I've been really interested in is to try and design for equity instead. So not necessarily focus on like demographic specific models. And sometimes you will find like demographic group, like different thresholds of decisions, for example. But if we really design the model, like knowing the biases in the data and design for equity, then like I do think maybe we can reach that compromise of like, you know, like not necessarily needing all of that extra information or having to navigate all of the legality of it, while providing a model that serves all populations but benefits most who just need the most.